close the door back there? Thank you so much. Okay, so front one, two. Is it inside this room or outside? That sound? The fan? Oh, really? Oh, okay. Thank you. So let's go over this. So first part was about this fill in the blank, okay, of all these questions. And this part, you see, it's like 1, 2, 3, 3 and 3 is 6, and 3, so it's total 9 out of 20. And the rest is like 11 out of 20. So it's almost like half and half. And I originally thought this was almost like giving you points, because this is something you already learned in your other course as well. And I thought this was a review, but surprisingly more than just a few. I expected you didn't have a concept about what this was. So I highly recommend that you guys go back and study this, and hopefully what we do today is going to be helpful as well, right? And by the way, for various reasons, because at the beginning of the semester we had some students who were affected by this nasty COVID, and I was out of town, and last week, like this month, Tuesday, didn't have class, so several lectures were recorded and uploaded on Folio. So you want to take advantage of those as well. Okay, please. Any of you watched the recent video, the lecture? Only you, too? Oh, come on! I was almost like dying and crawled out of bed to upload those. I was not a good student when I was in your age. I was a party guy, like I said, but I had to work like my ass off to recover all those things. So please, when you graduate, go out there, and if you're lucky to find a job, it's a jungle out there. You make a mistake, then you're fired. So please, while you're here, while you pay your money to learn these things, focus a little bit more and try to make the most out of it. Please, I almost like beg you guys, because you will regret later. Okay. All right. Anyway, let's go back and then try this thing together. So normal distribution, for a normal distribution, certain percentage of the observations lie between plus and minus 1 standard deviation around the mean. So if we have a normal distribution like that, and we have a mean value, and from here, this is going to be 1 standard deviation, 1 standard deviation, right? And we have 2 standard deviation away, 3 standard deviation away. We talked about these, right? And what do we have? This area between 1 plus and minus 1 standard deviation from the mean value, this is about like 70%, or more in detail, this is 68% of your total distribution, right? And this area is going to be what? 95%, right? And plus and minus 3 standard deviation, I told you this is going to be 99.7% or whatever, very close to 100. So please remember those. And this was about plus and minus 1 standard deviation, so it's going to be 68%. If you wrote 70% still, I put full credit for that, okay? And if there are resistors that follow a normal distribution with a mean value of 2 kilo ohm and a standard deviation of 140, okay, ohm, the lower and upper limits of the resistance value covering 95% of the observation will be this and that. So in this example, the mean value here is what? It's 2000, right? And this is 2 kilo ohms, so kilo is 1000, right? So it's 2000. And 95% range is what? This is plus and minus 2 standard deviation. So from here, you're going up 2 standard deviation, which is this here is 1 standard deviation. That was 140 ohm, was it? Yeah. Therefore, the value here is going to be 2280. And the value down there is going to be what? It's a 1720. Is that right? Yeah. Yeah. So this colored area is going to be 95% of the total area. Okay? So the value here, what I'm looking for is 12 this and 2280. Something like that. All right? So that's the range that covers 95% of the distribution. And then now we're talking about the z-score for a resistor that was measured as 2.2 kilo ohm is this. So the way we find the z-score is z is x minus mu divided by sigma, right? So my x is 2200 and my mu is 2000 and my sigma is 140. Okay? Therefore this is 200 over 140, so I don't know, it's a little bit greater than 1.5, something like that. Okay? I don't have the number with me, but you can find that. You get my point here? Okay, so the value is here, let's say 1.4. And then the next question is, this resistor of 2.2 kilo ohm may be located around, we need that value. Can anybody get this value? 200 divided by 140? 1.43? Okay, thank you. 1.43. Okay, so what we have here is, from here we have 2000 and the value we got is, here is 2200, right? And if we convert this into the standard normal distribution where we have 0 here, then this value will be converted into 1.43. And we're looking for this area, or yeah, it's asking what is this in top certain percentage. So this colored area is what we're looking for, or it's this here, or this value is 1.43. Therefore, we can search from this table. My z is 1.43, so it's going to be this and that. Therefore, this value, this colored area, is going to be 0.07636. Okay? Therefore, this is going to be 7.6% from the measurement distribution. Does that make sense? While I was grading, I see up to here, students were doing pretty okay, but from this point, you are getting confused, and these two, only like 2 or 3 students made it correct. Okay, so you are getting your z-score using this equation, and this is the real world, the resistors, or this guy, and from here you're converting into the z values, and based on that z value you're using this table to find out this colored area. Okay? All right. And then the next problem was about the z-score for a resistor that is in the bottom 5% of the distribution is this. And the corresponding resistance value is going to be that. So for this problem, what we're looking for is, we're looking for a resistor value here that makes this thing to be 0.05, bottom 5%. Okay? And the center value was 2000, so it's going to be a little bit lower than that value. That's what we're looking for. That's the resistance value we're looking for. The bottom 5%. Okay? On the other hand, in this table here, this table is only providing the value, the colored area that is above this whatever z-score. Okay, so what we would like to try is, we would like to find a z that makes this colored area to be 0.05. And this value and the value down here are going to be symmetric. This is 0.05, this is 0.05, right? And this is symmetric, so whatever z you got here, you just flip it over to put a negative sign, and that's going to be the value down here. Okay? So that's what we would like to try. And the z-score that makes this colored area to be 0.05, we need to find it from this table. So 0.05 is here. Where is that? Yeah. This is close to 0.05. 0.05050 or 0.04947. So let's just choose this one. And that one corresponds to this and that. So the z-score here that makes the area is 1.64. 1.64 makes the color area to be very close to 0.05. Okay? Then the bottom 5%, or the value here, is going to be minus 1.64 because it's symmetric. Okay? Therefore, the z-score, what we're looking for, is minus 1.64 or minus 1.65. I've seen many students put positive 1.64 here. Okay? Unfortunately, it has to be a negative value because we're looking for bottom 5%. Okay? So that's a small thing that I want you guys to understand. And by using this value, if you plug that in here, then you can find this guy. So z is x minus mu divided by sigma one more time. And my z is minus 1.64. Is x is I don't know. Minus mu is 2000. Divided by sigma is, what was the sigma? 140. Okay? Then we can find my x. X is, I don't know, it's 2000 minus 1.4 times 1.6, so it's a little bit greater than 200, like 250. Whatever. But the value here, let's say if my x was like 220, then the value down, the value down here has to have a number that is smaller than 2000. So the value you obtain here, you're looking for the bottom 5% of the distribution, which has to have a value that is lower than 2000. Okay, so you are looking for at 1800, 1900, or whatever, depending on the math you did. But it has to make sense. You're looking for something that is smaller than the mean value. Okay? So even though you made a mistake wherever here, if you got a value that was greater than 2,000, then you should think about it. Oh, it's bottom 5%, but that's smaller than the mean. So it's a little bit odd. It has to be smaller than that. Then you need to go back and check and update your stuff. Okay? Any questions up to here? I'm pretty sure at some point we will have something similar to this again in one of the midterm or even the finals. So please make sure you guys check. Yes, go ahead. No, but you can come to my office whenever, okay? You can just come to my office. It's in my office, so you can check your personal stuff. I don't, give them out and then collect back. It's a little bit of waste of time. That's my experience. Because more than just a few students don't care about their stuff. It's just, takes time to distribute this thing, takes time to collect back. And there was an incident who marked while it was out there, and I need to, and came back to me, hey, I wrote the right thing, and then quality control. Okay, so, but your stuff is in my office, so anytime you can come to my office. Okay, all right. Okay, any other questions? All right, if not, let's move on. Oops, this thing was imported wrong. All right, so the next part here was the RC circuit, and it's here and has a square wave with 4-volt amplitude. And the question was, find the time constant by using the following graph of the input and output voltage obtained by the oscilloscope, and explain how you determine the time constant value. Okay, so some of you already must have done this lab, so maybe it may have been easier for you to identify. Some of you who hadn't yet, maybe a little bit more difficult, but if you know the concept, this should be easy peasy. So it is starting from down here, and then it's going up and then getting saturated like that. Okay, this is the step input. Okay, and your output is increasing and going up, saturated up to there. So the time constant tau, how do you find that thing? It's the time it takes to reach up to certain percent of V infinity minus V initial. Excuse me. Anybody remember this number? 683, right? So then, excuse me. This here is what? It's 8 volt. It's starting from -4, going up to 4. So it's total 8, right? And we're looking for 63% of this 8. So 63 times 8 is 24, 20, 48, 50. So it's 5 volt. All right? So it is starting from down here, and it is rising up until we have a value. This is 5 volt. Okay? This is 8, and 63% of that is 5. So from here, it has to go up to 1 volt. So at this point, it is going up to 1 volt here, and that's 8.4. So this is 8.4, here is 7. Therefore, the time constant you can estimate as 1.4 second from your measurement. Okay, that's one way. What would be another way to try finding the time constant? So Yes, yes. So I guess what she was trying to say is it takes about 3 to 5 times of your tau until it gets saturated or in steady state, right? Therefore, let's say from here, it starts from 7 and it goes up to 11. So from here to there, it's 4 seconds, right? And then I told you this is going to be 3 to 5 times of my tau. So if you consider, hey, I'll just consider 4. So it takes 4 seconds, and that's 4 tau. Then I would say my tau is 1 second. Okay? That's fine too. All right? So 1.4 or 1.2 second, 1 second, or whatever value close to this, and you had a strong logic, then you're all good. Okay? Does that make sense? Any questions about this part? Okay, if not, let's move on. Next part is obtain the theoretical time constant. Time constant is RC. Okay, and tau is R is oh, these are gone. When you import the Microsoft Word, I believe it was 15 kilo ohm, and never mind. We'll just use some whatever numbers. So let's say the resistance was 15 kilo ohm and the capacitance, let's say, was 100 microfarad. Then this is 15 times 1000, and this is 100 times. Micro is millimicro, right? So 10 to the minus 3, 10 to the negative 6. So this is 10 to the negative 6. And this here will give us 1500, this and that. And this is 10 to the 3, 10 to the minus 6, so 10 to the minus 3. So this will give us 1.5 second, like this. Okay? So I kind of made up this problem. Like, theoretically, it's going to be 1.5, and when you actually measure it, it's going to be something close value to that. Okay? And then the next problem is approximately how long will this take to reach steady state response? And in seconds, so I told you 3 to 5 times of the tau. That's like a reasonable guess. So we got 1.5, so 4.5 to like 7.5 or seconds, something like that. We're all good here. Okay? And then the next problem here was sketch the Bode plot of the RC circuit shown above and indicate the bandwidth and the cutoff frequency values in your sketch. Show the values as well. So, Bode plot of an RC circuit, it's this. It's your horizontal axis is the frequency in log scale, and the vertical axis is V out over V in decibel unit. Here, surprisingly, there was nobody who made this graph correctly. I was a little bit surprised. Okay? I've seen some of the students put like this, and you put a frequency and you put dB like that. Well, this thing is almost correct. If you just plot V out over V in a linear scale, it may look like this, but if you convert this thing into decibel and if you convert this thing into log scale, then it's going to look like that. And Bode plot specifically needs to meet this condition. Okay, so this is the Bode plot. All right, I've seen students putting something like this, like a sine wave. I've seen something putting a step response like that. No, these are time domain responses that you see with your eyes. But frequency response is something you do not see. It is like a map. You are providing different inputs and you're checking what the output amplitude is going to be like. Okay? So it is very different from what you actually see with your eyes or feel. So this is the Bodhi plot, and it starts to bend down at this point, and that's going to be the cutoff frequency, right? Or you can use omega c, depending on whichever you choose. And your cutoff frequency is nothing but 1 over tau, and we found the tau was 1.5, so it's 1 over 1.5 radian per second. If you chose to use in hertz, all you need to do is just divide it by 2 pi. So it's going to be 1 over 2 pi 1.5, like that, and this is going to be in hertz. Okay? So, and then the bandwidth is nothing but the frequency from 0 up to your cutoff. So this is going to be your bandwidth. So your bandwidth is basically same as the value here got here. So that was what we were looking for. We were looking for the plot, your sketch, indicate bandwidth and cutoff in the graph here and this, and find the values. You get these or you get this. Okay? Any questions up to this point? Okay, now let's move on. Then the next problem was about plot both how the step response time and Bodhi plot, the frequency response of this RC circuit, will change if the time constant gets smaller. Okay, and explain this. So first, we would like to plot the step response and the Bodhi plot. You're plotting here, you're plotting that one more time. I almost tried to give you points here. So the Bodhi plot, again, it's going to look like this. This is log of your frequency, and this is V out over V in, and in decibel unit. And your step response, it was given here. Oh, not, it's this, right? So your step response rise up like that. This is time, and this is voltage. Okay? Same thing. Same thing. And this one particularly, I see many students, it was not that many, but like at least I remember 3 or 4 students left it as a blank. Okay? I honor your, honesty about not knowing this, but I would like to say just try your best. If you leave it as a blank, it makes it very easy for me. Like it's grading. You can save my time for grading. It's 0. Boom. I can move on. I don't need to think about like giving you partial credits. But I want you to try rather than just putting a blank there, like a samurai, like killing themselves. No, please try, okay? So these are the step and the Bodhi plot. And then what do you want to check? We want to check how the graph here will change as the time constant gets smaller. And then I want you to explain it. So you guys explained it well, and the way it may change is it's going to go like this. It rises up quickly as we have a smaller time constant, and as we have a smaller time constant is getting smaller, then that means this guy is getting larger. the point where it starts to bend is going to be more and more towards this way. It's going to go up like that and then bend. It was going to go up like, and then it will go up, and then it will start to bend like this. The point it bends is going to get larger and larger. You're going to have a broader bandwidth, broadband. Okay, so if you explain those and even draw those here, then you got full credit here. Okay? All right. And if you need to cut the time it takes to reach the steady state by half, what's going to be the R value? Okay. You need to select while keeping the C the same. Tau is what? RC. You need to cut this thing into half. Then this guy needs to be in half. Right? So whatever R we had, I think we had 15K, right? Yeah, 15K. Then here we're looking for 7.5 kilo ohm. I see many of you did this thing correctly, which was a good sign, but still I saw some of you put like 30 kilo ohm, the opposite way. And that's what I told you. Like, you need to have this good sense, because when you're making decision, do you need to increase, decrease? Do you need to turn left or right? Those answers you need to answer correctly. Okay, so we are trying to cut the time constant to be half. Then this guy needs to be small. Okay? Any questions up to this point? Okay, if not, so let's move on. And finally here, for a rectangle with width 5 plus or minus 1, 0.1, and the height 2 plus or minus 0.05, okay, and find the uncertainty of the area of the rectangle using most probable error. And this one, many of you did this thing correctly, which was a good sign, and I just updated the numbers from my lecture note here to save a little bit of time and show you. So this is the lecture note we had before, and the RSS value, where's that? Most probable error is obtained like this, right? And we actually tried an example problem using trying to do this volume of a cylinder. So instead of that, we just change it to the area like this. So area is, forget about this guy, we have width and height. Okay, so width times height is going to be 10, because yeah, we do have it down here. We have 5 and 2. And for this RSS, this is the equation. So for this function, we find the derivative for the first variable, derivative for the second variable, the uncertainty for the first and second, and then we square those, and put a square root like that. So this function was nothing but w times h. So we put w times h here, and this term, w times h, with the derivative with respect to w is nothing but just h. For this one is nothing but w. So from here, you can just plug in these 10, 5, 2, 0.1, 0.05, like down there, and you're going to get this value. Okay, so it was just a simplified version of the example problem we had in class. So if you guys want to take a look at this more time, I highly recommend that you just go back to your lecture note and try to update the numbers and do it on your own if you're not really sure. Okay? Any questions here? not